From the University of Chicago, this is Big Brains with Paul M. Rand. Conversations with pioneering thinkers that will change the way you see the world.
Imagine a world in which the usual rules of physics no longer apply. Particles act in strange ways, they can float through walls or even remain connected, even if they're miles apart. That's the fascinating subatomic world of quantum engineering, and scientist David Awschalom of the University of Chicago's Institute of Molecular Engineering is working to unlock quantum secrets and apply them to new technology. His research could help turn the stuff of science fiction into reality, from superpowered computers to unhackable codes to the ability to peer inside the human body at unprecedented scales. I hope you enjoy our discussion as much as I did. Well, David, glad to have you with us today.
It's a pleasure to be here.
I think you are our first expert on quantum physics and engineering to come and speak to us, and there's a reason why you're our first. And the biggest part is I'm a little intimidated by the subject because I think I understand parts of it, then realize how little I actually understand.
Well, we're going to try and make you feel better.
Well, maybe at the most simplest form, if you can help me understand what quantum physics is, and even more so, why is everybody talking about it today and putting so much energy into it?
Well, at the end of the day, quantum physics really is just a set of rules that describe how nature operates at the very smallest scales. So, the world at our scale, human-sized scale, it's a little bit like looking at a big puzzle, a big picture. You see the image, but you don't necessarily see all the individual parts that come together that make it what it is. And if you take this puzzle and you start to break it into smaller and smaller pieces, eventually you get down to a piece that you can't break any further. And the overall picture is based on how those little pieces come together.
And help me understand, it's also if I understand particles and waves, is that right?
Well, matter and energy are a little bit like this picture we're talking about. They can also only be broken down so far till you get to the level of atoms, electrons, or particles of light, photons. And when we study these individual pieces in nature and how those come together, that's quantum physics. And the behavior of those tiny pieces is unlike anything we see in our world, in the human scale world, right? Our world is deterministic. If I throw a ball, you know where it's going to go. If I pull a wagon, you know how it's going to move. But at the atomic world, things don't work that way. Wagons can go through walls. Wagons can be entangled. They can share information in ways that are hard to separate. And it's these funny, exotic rules of matter that are leading to a new technology. One of the most challenging aspects of this technology is that what drives it is extremely counterintuitive.
What do you mean by that?
We don't experience the rules of quantum mechanics in our everyday life. And to develop intuition about how you build a quantum technology based on rules we never experience is a challenge.
Can you give an analogy about what you mean like that?
Sure. If I ask you to design a really good diving board, you could probably intuitively do it because I'm guessing you jumped off a few diving boards.
A few cannonballs in my day.
I'm guessing.
Okay.
So you have a sense that, it's going to be a plank, it'll be nailed down at one end, it's sort of going to work, and you can calculate a few properties. But if I ask you to design a quantum system where particles will be entangled and interact, there's no intuition. You don't see it. You don't see it on the sidewalk. You don't talk to people about it. So you have to develop a feel for this, the way the world works that we don't experience or see. But in fact, it is the basis for our world, and that's a challenge.
Why are people so excited? It feels like there's a bit of a race, if that's the right word, going on to develop capabilities in these areas. Where is this interest coming from? Why are people as motivated as they seem to be?
Well, I think it's important to appreciate that this emergence of a quantum technology isn't to replace our existing technology, but to offer new capabilities.
Okay.
And that's what's excited people in ways that maybe at first blush don't seem obvious. So, for example, a quantum state is an extraordinary sensor. So one idea that's been emerging is, could you take magnetic resonance imaging, right, that many of us have been exposed to today in hospitals, and improve its resolution hundreds of millions of orders of magnitude? Instead of looking at a large number of nuclei, which is done today in an image, roughly 10 to the 20th, billions of nuclei. Imagine you could see one, which you can do with a quantum sensor. Suddenly, one could begin to unravel the mysteries of proteins, for example, in the human body, their structure and function relationship, which would revolutionize areas of The way we communicate today, the way we purchase things on the internet is based on encrypting our information and our personal information. It's based on codes that in principle could be broken with quantum technologies. On the other hand, quantum technologies work to a large degree on the uncertainty principle, which I'm sure you're familiar with.
Who isn't?
Of course, the act of looking at something can change it. So that might seem a liability, but it's actually an asset for communication. If I send you a message, you would like to be sure no one has been eavesdropping. So one can use this active observation as a way to preserve information being sent and enhance our personal security for information.
Are there things in the national security realm that there is hopes to work on developing?
Well, I think quantum communication is one of many things that's of interest to the federal government. And, right now, all of our currency exchange and purchasing with, you go online, you use your credit card, you see the small lock symbol on Internet Explorer or Google Chrome, and your information has been encrypted using a certain algorithm into a code, such as your Visa card, and then transmitted, to a financial institution. If a machine appears that can break that code, which quantum computers may well be able to do, then you're at risk nationally from a security perspective of your information being transparent. So it's very important to think about building quantum communication channels that are far more secure.
So that actually sounds like a bit of a chicken or egg. And so there's the security side of this, while at the same time there may be efforts underway to create something that could break existing codes using quantum.
That's correct. So quantum machines and quantum computers in some ways will not work as well as today's computers, but for other applications will work extremely well. And that has to do with code breaking. It has to do with what are called optimization problems. And that means how do you organize the thousands of aircraft approaching an airport, to enormous business decisions. How do you prepare bids? How do you decide what to buy? Very complex problems. Quantum machines are very good at this. On the flip side, they can be used to do code breaking. So when you know a technology is going to appear in the next decade with this type of power, it's also important to prepare and to think about new ways to prevent possible applications of technology that may impact national security.
So when we talk about quantum computing, the closest example that I began somewhat getting my mind around was that the ability to compute on many different levels at the same time.
So in a way, that's right. And the difference is entanglement, this property we discussed a little earlier, the fact that multiple particles can be sharing information. And this entanglement, this exotic property of quantum mechanics, means that computers built on that technology will scale very differently. And I'll give you an example. So today, let's say you had a computer with just 10,000 transistors, and that's very tiny. Today, the chips in your iPhone will have hundreds of millions of transistors. But let's say you had just 10,000.
Okay.
If you want to double the power of that chip, you add another 10,000 transistors. In a quantum machine, let's say you had 10,000 quantum transistors, or qubits as they're called, quantum bits. To double the power of that, you only need to add one bit. So you might see where this is going.
I do.
If I had 10,000 quantum bits and I added 10,000 quantum bits, I would end up with a machine 2 to the 10,000 times more powerful.
Okay.
Not twice as powerful, but 2 to the 10,000 times
remarkable.
more powerful.
So personally, the things that you're most excited about maybe seeing within your lifetime that can be achieved?
The truthful answer to that is no one really knows. When the transistor was discovered many years ago at Bell Laboratories, and the transistors were about a good fraction of the size of your fist, no one imagined you would have 700 million of them produced on a chip for $100 and how it would revolutionize people's worlds. So we're at that stage now where we have a few transistors.
Okay.
And you're asking a great question. Where will it be in 10, 20 years? And to people working in this field, I would argue one of the most exciting things is we really don't know, but it's going as a field so fast, so well, already in interesting directions like sensing and communication, beyond computing, that while it's not obvious where the biggest impact will be, it's very clear there will be big impacts. And the example I gave you in medicine, even magnetic resonance imaging, that alone would be such a big impact on society. It would be extremely exciting.
If you're listening to Big Brains, there's a good chance you consider yourself a lifelong learner. However, you may not know about the University of Chicago's Graham School and its focus on continuing liberal and professional studies. For more than a century, Graham has been a destination for lifelong learners. They offer courses online and in the classroom, bringing the transformative education UChicago is known for to students of all ages. To learn more about the courses, certificates, and degrees, visit graham.uchicago.edu. What is different about this, and why is this a new field? And how did we first realize that there was something different than we understood there to be before?
Well, I think what's happened in the last decade or so is scientists around the world have become surprisingly adept at controlling these individual pieces of matter in ways that were unexpected. By using light, electric, magnetic fields, experimental techniques have been developed where you can literally get to the level of individual photons, individual electrons, and nuclei. And the tricky thing here is our technology today is based on the fact that electrons have a charge. So when you turn your light switch, the light is on or off. It's 0 or 1. But in the quantum world, these electrons have another property, which is called a spin. That is a little bit like the Earth revolving around the sun. The weird thing is that that spin can point up or down or any combination, an infinite combination of them all at the same time.
We knew this back from Einstein's earliest days. Is that where the first concept of quantum really started coming from, or was it before that?
No, you're absolutely right. I mean, people began to realize there were a number of properties of light that were difficult to explain using classical physics, which from the times of Newton and onwards described a lot of our everyday life. But when people began to look harder and harder at properties of matter like the spectrum of light, the colors of light coming off from hot objects, people began to realize you couldn't explain that with the normal rules of physics. And eventually, from experiments like those and many others, emerged the fact that particles of light could be both particles and waves and have these dual properties, and launched this field of quantum science.
And so in the last 10 years, what is it that actually changed?
People have been discussing ways that one could exploit the quantum properties of matter for some time. And in the last several decades, people have been even thinking about how you could store information using the quantum states of matter. And I think the trick has been how. How could you turn this from science into engineering? How could you build something that would extract these quantum properties and use them in imaginative ways? And what's happened in the last 10 or 15 years is that people have come up with very clever ways of doing this. Trapping atoms, using superconductors, using particles of light, building structures on the atomic scale, using advanced lithography techniques, which are ways we make our circuits today, that could capture and control many of these properties. And then use some of their exotic properties to build new technologies.
So let's go back a little bit. How did you start in your career? And since quantum is a relatively new field, when did you pivot over and start deciding this is something that you want to specialize in?
So I began research at IBM in the days when it was a monopoly and could fund a basic science laboratory. And I was working with a group of colleagues trying to understand the dynamics of electrons. That is, people began to understand the properties of matter at a certain level. And then there were many theories to explain what people saw. But there were very few experimental techniques to dive deep down into matter and watch electrons move. Look at the spin of the electron and directly measure it. And so
at that time, what were you looking at specifically? Better computing?
No, we were looking at what would happen when you try to move information from one electron into one magnetic atom. The goal was, could you think about building storage technologies that would be just a handful of atoms? Okay. What was the limits of information storage? We designed an experimental technique, and we watched electrons move their spins into single atoms. But the big surprise for us was the control experiment. At the end of this big process, we just looked at a standard commercial semiconductor. And we found that the spin of the electron could be created and maintained for surprisingly long periods of time. It was a huge surprise. And it launched this field of quantum spintronics.
So what brought you here to the University of Chicago?
What brought me here was the realization that this was becoming a new discipline. It became clear that this career was developing in a very unusual way. It was integrating physics, material science, electrical engineering, computer science into a new discipline. And what was attractive about the University of Chicago was the opportunity to build an applied science program around a very new discipline, to start from the ground up as a new way to create a workforce, quantum engineers.
That sounds rather intimidating. How do you get your arms around how to do something like that?
With a lot of help.
Okay.
With a lot of colleagues here and a lot of help from the University of Chicago to build beautiful laboratories and to hire a group of new faculty that think very broadly, work collaboratively, cross the normal disciplines, and use this as a magnet to attract some of the best students in the world.
And how does what you do tie in with the Institute for Molecular Engineering here at the university?
So the Institute of Molecular Engineering is built in very different thematic areas. There are several themes, and one of the first was quantum engineering. And as the Institute grows, it's becoming clear that projects, say, in quantum sensing are playing a role in water, or molecular engineering, or bioengineering. And now people are asking many questions about this. For example, in chemical reactions, what is the role of quantum mechanics? In photosynthesis, is there a quantum process and can you control that? Can that be used to create better batteries, better energy sources? In the way the mind works, is it crazy to think about a quantum process playing a role in how the brain functions? Is that a crazy thing to think about? 20 years ago, that might have been viewed as absurd. And today, people are beginning to think about this.
Is Chicago distinct in how we're approaching it?
There are many good research institutions working in this area now. I think Chicago has a very unique platform to build a world-class quantum engineering program. And I believe we've already done this by starting from nothing. What's unique here is to think about this not as a physics department or a chemistry department, but as a scientific problem that requires different expertise working together to rapidly advance the field. And what Chicago has that's also very unique are two world-class national laboratories, both Argonne and Fermilab, and taken together, there are dozens of scientists working in this field, all of whom can work with the students and build something very special. And to that end, this is an extraordinary opportunity for them to use the resources of national labs with the academic expertise of the university and open it up to the nation at large.
Energy powers our modern world, fueling innovation and improving living standards across the globe. But it's one of society's greatest and most complex challenges to deliver access to reliable and affordable energy without putting our health, environment, and climate at risk. For a deep dive into today's policies and trends driving solutions to the global energy challenge, listen to Off the Charts, a podcast of the Energy Policy Institute at the University of Chicago. We'll provide analysis from UChicago experts, as well as government and industry leaders, all grounded in the latest data-driven research. Listen on our website at epic.uchicago.edu or wherever you get your podcasts.
My understanding is that from a governmental perspective, there is an increased interest in some of the work that is going on in this field, and there's increased research dollars coming into it. Is there anything that you can talk about what's happening and where you see that going?
So a number of us have been working for the last 2 years on developing a national initiative, which is referred to now as the National Quantum Initiative, where the intent is to have the federal government help drive this emerging technology, and in particular, how you bridge this gap between discovery-driven research in universities and a practicing technology. You need a middle ground to try and move basic research into test beds, how you begin to build systems. And the idea is to use the national labs and universities together in a very organized way to accelerate progress in the field. So you're right. Virtually every federal agency is now creating a quantum technology program or enlarging their own quantum technology program.
So as an educator, how do you think about this from if there's a program and students are studying, for lack of a better word, traditional engineering or traditional physics programs? Do they continue doing that? Or is it, if you really want to think about positioning yourself for the future, thinking about it from a quantum perspective is going to be a far more progressive way of positioning yourself?
It is a more progressive way of approaching education. It's not that it's the best, it's different. And there's nothing wrong with the traditional track in physics or electrical engineering or computer science. But in the quantum engineering field, you need all of these skills, or a large fraction of them, to really make substantial progress. And to that end, you need to think differently, and the training is a little different. And one of the ways we're helping to drive these programs is also to think about how do students train differently. So we have launched here a project with the National Science Foundation called the Triplet Program, because each student has two advisors, one in academia and one in a company or a national lab. And they will be doing research of interest to both parties.
Wow.
And work between both institutions. And there, they will have the advantage of understanding how science and engineering work in a major company and a university, and how you exploit the interface between the two to do something very unique.
Well, it's a very fascinating field at a very early stage. And what makes it particularly compelling is when you think, even saying, what do we think can be achieved 5 years out, that it's hard to answer that.
That's exactly right. We joke it's a little bit like driving 100 miles an hour on a road with just your low beams. We're trying very hard to stay on the road right now. The car is going very well, very fast with no problems, but we're not exactly sure where the road is going.
Okay. Is there anything about all this that makes you a little bit nervous?
No.
No.
I think discovery-driven science is an extraordinary opportunity and a privilege to pursue. And I think one of the things that the students here are finding is it genuinely is exciting not to know all of the answers and to learn as you go along. And I think we'll see how things evolve down the road.
All right. Well, a lot of fascinating things. We're going to keep an eye on what's continuing to develop. Thank you for coming in and spending some time talking with us.
Well, thank you very much for having me.
Big Brains is a production of the UChicago Podcast Network. To learn more, visit us at news.uchicago.edu and subscribe on iTunes, Stitcher, Google Play, and wherever else you get your podcasts. Thanks for listening.